Welcome back to the Signals and Systems lecture. My name is Jong Park. Okay, now we are dealing with chapter 2, and in the previous lecture we have studied about the sinusoidal signal in both continuous time and discrete time. We talked about the period and the time shift, stuff like that, and we compared the characteristics of the continuous time and the discrete time. And today we will talk about the exponential functions, and the first one is about the real exponential signal. Okay, so let's start with the continuous time case. And for the continuous time, the equation expression for the real exponential can be expressed as follows. So we can say it as c times e to the a multiplied by t. Obviously, t is the variable which is related to the time, and c and a are the real number. So c and a are the real number, and e, as you all know, is a Euler number. So, and the value goes like 2.71828 blah blah blah, something like that. And if we plot this equation in the xy plane, and x as a time value, then depending on the value of a, the shape changes. So if a is bigger than 0, then the exponential function grows as time goes on. So like this shape. And if a is smaller than 0, so if it is negative, then it's a decaying function, and both meet at the y-axis, whose value is 1. The value is 1 here, and I can say that it's a growing function if a is bigger than 0, and decaying function if a is smaller than 0. If we examine the time shift as we did in the sinusoidal signal, if we do the time shift, we can modify the previous equation by putting t plus t0 in the value t. Then it becomes as follows. And if you divide these two and put them in the separate term, then this becomes c e to the at0 and e to the at. you can express this term like this. When we studied the when we studied the time shift in sinusoidal continuous sinusoidal signal, the time shift can be interpreted as the phase shift, remember? But in this case, if you shift this real exponential signal in time domain, then maybe it becomes like this. And this time shift can be thought as a scale change. Like if you multiply the original function by some constant, this constant, it can be seen as a scale change. So with respect to the real exponential signal, the time shift corresponds to the scale change, not phase change. And the other way around is also possible, so we can do it in both directions. So you have to see the difference between the sinusoidal signal and the exponential signal. Okay? So like based on the sign of t0, the scale can be either get large or get smaller. Both ways possible. And about the discrete time, we can write down the equation similar to the continuous time as c times e to the beta times n. And we can also express this as c times alpha to the n, where alpha is e to the beta. So when you substitute this equation into this term, then you obviously get this, the first equation. And to make the point clear, the real exponential, the term real means c and alpha are real. Okay? And you can write this relationship in terms of beta, which will now include the natural log of alpha. Okay, so in some textbook, the natural log is written as ln, or we just say it as in other textbooks, we just say log of alpha. And if nothing is on the base, nothing is on the base, then you just think that as a Euler's number. So like this. And I think many of you already know that if the base is different, then you have to write down the base like this. The log, like for example, the log of 2 when base is 10, like this. Okay. If there's nothing on, or if it is written in ln form, then this is obviously the log where the base is e, the Euler's number. And since I don't really want to plot the discrete time case, I am going to import a picture here. So since it is a discrete time signal, we can see that the signal is discontinuous. And if alpha is bigger than 0, which means with this equation beta is a real number. Okay? Because obviously the log equation goes like this, and if alpha is in the positive side, then you have the value beta with this relationship. So if alpha is bigger than 0, then it is about this right hand side graphs, and if depending on the value of alpha, if alpha is bigger than 1, then it is a growing function, and if the alpha is smaller than 1, then it's a decaying function, similar to those with respect to the continuous time case. And interestingly, if alpha is smaller than 0, then as you can see with this log graph, if alpha is smaller than 0, there is no equation. Excuse me, there is no solution. Therefore, you can say that if alpha is small, if alpha is negative, then the beta is a imaginary number. In Korean, you say this as hosu, okay, and this is shilsu. So, as I mentioned earlier, the term real corresponds to the real number of C and alpha, not beta. Beta can be imaginary depending on the value of alpha. So therefore, obviously, C times the form of C times alpha to the n is more likely to be seen as a real exponential, because you don't want to put the imaginary number here to confuse the others. So when alpha is smaller than 0, if this value is negative, then depending on the integer, the signs get reversed. So if you have an even number, of n, then you have the positive sign. And if you have odd number as an n, then you have the negative sign. Therefore, the sign gets reversed, and if alpha is smaller, if the absolute value of alpha is smaller than 1, then it kind of decays, and if the absolute value of alpha is bigger than 1, then it grows as n goes to infinity. So please notice the difference between these four figures depending on the value of alpha. And in summary, even though beta can be an imaginary number, we call it a real exponential because c and alpha are real. I think you should memorize that. And if you combine real part and the imaginary part, then you become a complex exponential function. Oh, I think I'm gonna write something down between these two, so I will start the new subtitle here. So complex exponential in continuous time we can write down the same equation as we did with the real exponential in continuous time, which is x equals c times e to the at. But when we were dealing with the real exponential, this c and a were a real number, but now these c and a are complex numbers. Okay, so let me assure that. Okay, and before we move further, I would like to talk about the expression. I would like to talk about the things how to express the exponential number. So let us have a line here. Say if we have the value a as the real part as 2 plus the imaginary part as 3. To express this 3 as an imaginary part, you often express the term imaginary as j or I, but I will prefer j here. Oh, and by the way, j is square root of -1. And when you express this complex number, you have to draw the xy plane where the x-axis is the real number, real axis, and the imaginary number as y-axis. Then this thing right here is called the rectangular form. And with the rectangular form, you can express the complex term as a real part and the imaginary part separately. So if we plot this graph, plot this number, then we have the real part of 2 and 3. So we have a point here which represents the value a. And also there is a polar form where we express the complex number as the magnitude and the angle. So the rectangular form was like a equaling r plus j omega, and the polar form is representing the value by the magnitude, where you express the magnitude by the bars here, and then e to the j theta. So this is theta in Greek letter. Maybe you can distinguish them by writing this way, but in my writing I always write theta like this, so I'm very sorry about that. Please don't be confused with other letter. 죄송합니다. 제가 그 세타 그리스 문자 세타를 원래 이렇게 써야 되는데 저는 이렇게 쓰는 버릇이 있어가지고 이제 앞으로도 헷갈리지 않으셨으면 좋겠네요. 저는 이미 돌아올 수 없는 강을 건너서 이렇게 쓰는 습관이 돼버렸으니까 저는 이미 끝났고요. 여러분들은 예쁘게 쓰시길 바랍니다. 저는 이미 끝나서 어쩔 수가 없어요. So in polar form, this refers to the magnitude, and this theta here is an angle, or maybe sometimes someone call this as a phase. Okay, so the reason why I draw this thing is, with the rectangular form, you just count the value of real part and imaginary part respectively. But with the polar form, the distance from the origin to the value here, the distance is the magnitude. So this right here is the magnitude, and the angle between this line, this blue dotted line, and the plus x-axis is a phase, which is represented as the theta. And you can either express the complex term in the way of polar form or in the way of rectangular form. So, okay, I think I will do one more thing. Excuse me. So we can relate this rectangular form and the polar form. For example, the magnitude C bar can be obtained by R and W, because this length is R and this length is omega, excuse me, not W but omega. Then C can be obtained by using the right triangular formula. So this is square root of R squared plus omega squared, and also tangent of theta can be expressed as the omega divided by R. Therefore, theta is arctangent of omega over R. Okay, so we can express like this. And also, R can be obtained by using magnitude and theta, which relates R as a cosine relationship. So we can write this thing as magnitude times cosine theta, and omega can be obtained by using the sine relationship. So C times sine of the angle. Okay, so we can obtain either parameters by the other values. So we had a break time reviewing about the rectangular form and the polar form of the complex number. Okay, so back to the complex exponential in continuous time. We had a review of rectangular form and polar form because we want to express these two C and A complex number in different forms. I would like to convert this C value by the polar form. So C equals the magnitude of C and the angle, which is e to the j theta. And on the other hand, we will express this A as a rectangular form. So two different ways for two different values, parameters, excuse me. So A being the real part plus J times imaginary part. And with the help of these two, we can write down xt as follows. So C becomes the polar form, and the e to the at, where A is a rectangular form, can be written as follows. Now obviously we can bound these two because they have j term here. So we can rewrite this equation by separating these two, and I will write this down, this one first. E to the r times e to the j theta plus j omega t, so I can bound them by j. Then excuse me, I will write down 0 here. Omega 0 t plus theta is the one which inside the parenthesis. And we will use the Euler's relation which is defined as e to the jx corresponds to cosine x plus j sine x. So I'm going to use this formula to the last term here. And we can say that xt is c times e to the r times cosine of omega 0 t plus theta plus j sine omega t of theta. Is it correct? And then we can separate these two again. So let me write down the final expression. Like this. And obviously there is a j here, therefore this is kind of like this is a rectangular form we did, and this part right here is a real part, and this part right here is the imaginary part. And you can say that the only difference between the real part and the imaginary part is the cosine and the sine function. And they have 90 degrees phase shift. Okay, as we already studied about the phase shift, you can see that we already did this. The phase shift between cosine and sine is 90 degrees. In radian, it's phi divided by 2. And therefore, these two have 90 degrees phase change, I would say. And if you plot this equation in the time axis, in the time domain, then you would have this kind of graph here. Depending the shape depends on the value of r. R is right here. I think I made a mistake. I forgot t here. I have to multiply r to t. I'm very sorry. So this one becomes rt, and rt. Okay. 제가 계산 실수를 많이 하는 편이니까 이런 식으로 제가 유도를 하다가 만약에 제가 영상 중에 끝까지 발견 못하는 게 있으면 항상 그 메일로 알려주시기 바랍니다. 그러면 제가 다음 그 시간에 고치도록 하겠습니다. 지금은 뭐 발견을 했지만. So if you look at this equation here, then there is t inside cosine and sine function, and there is t on the top of the exponential term on both. And if you just see the real part here, no matter what value t has, the cosine of something is bounded between -1 and +1. Okay? So the minimum and maximum value of cosine is -1 and +1. And therefore, the growing or the decaying of this function is determined by this exponential term here. If r is bigger than 0, then obviously this complex exponential grows as time goes on. And if r is smaller than 0, then it decays as time goes by. The envelope here, represented by the dashed line, these two envelopes, we can express this envelope as plus minus because we have two envelopes. This can be done. This envelope can be represented as plus minus c times e to the rt, where cosine term is replaced by +1 or -1, because the maximum value of cosine we all know is +1 and the minimum value is -1. Okay, so we can obtain the equation for the envelope here, and the second this picture is also called a damped. It's just a term, damped. sinusoid. The word damp, maybe you are already familiar to it, but we can define this damping as the influence upon a system damping is an influence upon a system which has an effect of reducing oscillations. You can have many definitions, but one of them you can write it like this. So there is also a term called damping ratio, which is used in designing a controller or in other fields. And like if you have a property of damping in a system, then it reduces the oscillation, as you can see in this second figure. And we are dealing with right now about the real part here. We can only draw in the two-dimensional space with one axis being time. Then we can only draw the real part. Then some of you want to ask me about what's the meaning of the imaginary part in this wave. So xt is kind of like a wave function, but what's the meaning of the imaginary part? Some may ask me that, and I would say that there's no physical meaning at all. This is the abbreviation for the equation, and I can see that there's no physical meaning because obviously it is a imaginary part, and we use this term because of the convenient algebraic properties and differentiations and integrations. These are some of the reasons why we use the imaginary part. Let's say, for example, if y equals x squared plus 1, then obviously you can say that there's no solution, correct? Because x squared plus 2, y equals x plus x squared plus 2 graph goes like this, where the minimum value is 1 at x equaling 0, and you can never hit the x-axis, which is the solution for this equation. Therefore it does not have a solution. However, with the imaginary axis on the other dimension, then we can get a solution. So if we equal x to the x squared plus 1 to 0, then the solution for this is plus minus square root of minus 1, which is plus minus j. And we can get this equation only if we consider the imaginary part. So in real part, it does not have a solution, but if you extend this equation to the imaginary axis, so one more dimension. So this is like a two-dimensional space where it has x and y axis, xy plane. But if you extend another axis, like j-axis or z-axis, then you can get the imaginary axis. But physically, it does not mean anything, but you can think of it as in this way. And also, one more example. We already talked about the e to the j omega t, where we can express this as sine and cosine by the Euler's relation. And with this information, we can verify the real part of e to the j omega t as cosine omega t, and imaginary part of the e to the j omega t as sine omega t. And the sinusoidal, this kind of sinusoidal motion, we can say it as a projection of circular motion onto any straight line. So if we have a circle here, we're talking about this right now. If we have a circle here, and circle, the signal rotates on this circle, as time goes on, and if you extend this, behavior, with respect to the timeline t, then it may goes like this, right? I'm very sorry, my drawing is terrible. And you can think of this real part right here by projecting this circular motion onto the real axis. So if this part right here belongs to the real part, and if you project this whole thing onto this real part, then maybe, I don't know, maybe it goes like this. And this is a cosine of omega t. And if you project this circular motion onto the imaginary part, let's see if the imaginary part belongs to this wall. Then the projection, I don't know, maybe think of like this, which is represented by the sine of omega t. And in the previous figure, these are the only trajectories which is in the real part. Okay? So let me write down what I said. 조금만 더 설명을 드리면 이제 그 허수 값이 도대체 뭐냐라고 이제 궁금해하는 경우가 있기 때문에 허수가 도대체 뭘까? 허수에 어떤 개수가 있다는 게 뭘 의미할까라고 할 수도 있는데 이제 우리가 보통 그림을 그리는 이렇게 그 시간축에 대해서 그림을 그리는 거는 당연히 그 이제 실수 부분에 대한 거를 그리게 됩니다. 왜냐하면 허수를 우리가 그릴 수가 없으니까. 그러면 얘는 도대체 뭘 의미하냐라고 할 수 있는데 걔는 이제 아까 유튜브 영상에서 보셨듯이 우리가 만약에 그 실제 존재하는 허수축이라는 걸 끄집어낼 수 있으면은 그때에 그려지는 트래젝토리를 의미하는 것이죠. 그래서 실제로 이 녀석도 이제 그 얘가 이제 어떤 원 운동을 대표하는 녀석이거든요. 그래서 걔를 시간축으로 쭉 끌어당겼다고 쳤을 때 그 3차원에 있는 녀석을 그 실수 파트에 대해서 정사형시킨 게 코사인이고요. 그리고 그 나머지 부분에 대해서 imaginary part, 허수 부분으로 정사형시킨 게 사인이 됩니다. 그래서 이제 이걸 우리가 3차원으로 대변했을 때 제가 지금 보라색으로 표현한 벽이랑 그 밑에 그 초록색으로 표현한 벽이 직각이에요. 여기가 직각인 겁니다. 굳이 표현을 하자면 3차원상으로. 그래서 직각인 이 의미가 뭐냐? 얘네 둘 사이에 위상 차이가 90도다 라는 의미니까 제가 여기서 써놓은 거랑 똑같은 게 되겠죠. 그래서 이 부분을 조금 더 얘기하고 싶어서 이제 imaginary part가 조금이라도 여러분한테 더 와닿았으면 좋을 것 같아서 이 부분을 말씀드리고 싶었습니다. Okay, I think we will move on. So the next topic is about the complex exponential in discrete time. Okay. So it's discrete time case now. And now here comes the squared bracket. And we will have the same expression as the one in real exponential for discrete time, which is c times alpha to the n. Okay, and here we have c and alpha both being complex numbers. So this is the difference between the real exponential and the complex exponential. Whereas c and alpha are real numbers in the previous study. Okay, and we will transform these two parameters both in polar form. Okay, with continuous time, we have used polar form and rectangular form respectively, but we will use polar form for both parameters. So C can be transformed as magnitude of C e to the j theta, and alpha as magnitude of alpha times e to the j large omega 0. Okay, we will use these notations. And then xn can be rewritten as like this, to the n. And if we sort this equation by the magnitude and the exponential term, then this would become like this. If we sort by j, then large omega 0 and plus theta will be the one in the parentheses. And since I don't have any space, I will copy this to the next page. And we will again use the Euler's relation for the exponential term. There will be cosine of omega 0 n plus theta plus j times sine of omega 0 n plus theta. So the final expression for the discrete time case is, magnitude of c times magnitude of alpha to the n cosine of omega 0 n times plus theta plus j c alpha n sine plus theta. We can say it like this. And if you draw this equation, you will get what will I get? I think this one is the right figure. So, as always, depending on the value of alpha, right? Because C is not, the magnitude of C is not related to n, and sine and cosines are constrained already, so the growing or decaying phenomenon depends on the value of magnitude of alpha, okay? So if the magnitude of alpha, which controls the alpha right here, is bigger than 1, then it's a growing exponential. And if the magnitude of alpha is smaller than 1, then obviously it's a decaying exponential. Okay, now we have obtained the complex exponential equation, and we have obtained the complex exponential equations for both continuous time and discrete time. If the complex exponential in continuous time has zero value for r, then what happens? Okay, I'm not going to rewrite the equation here, so I'm just gonna copy it. This was our final equation for the continuous time. And if r is 0, then this becomes 0 and e to the 0 is equals 1. So this term goes away and also this term goes away. So we can move this term like this. And as you can see, real part and imaginary part separately, and if r is 0, then the real part is periodic, obviously, and the imaginary part is periodic. So the complex exponential can be seen as a periodic signal. Okay? On the other hand, if complex exponential in discrete time has the value of 1 for the magnitude of alpha, then what happens? So I will fetch this equation here for the convenience and paste it right here and see if what happens if the magnitude of alpha equals 1. Obviously this term gets cancelled and this term gets also cancelled because 1 to the n equals 1 no matter what value n is. So we once again move these terms to the left and then we can get this equation. And even though we have this equation, can we say that this equation is periodic? Oh, we can also say this as, no, I'll just leave it this way. So my original question was, is it a periodic signal? To be periodic, as we already studied, the large omega n should have the following relationship, which was omega 0 n should equal the multiple of 2 pi, where both large n and m should be integer. So this kind of complex, even though the magnitude of alpha is 1, so the point is this: even though the magnitude of alpha is 1, the complex exponential in discrete time signal is not always periodic. It should have the relationship of this additional term. However, in continuous time, as r equals 0, then it is always continuous. Okay? And with this result, periodic, not always periodic. And with the continuous time result, I would really like to add that you have to note that some of periodic signals, periodic functions, are not always periodic. What should they have? They should have, each term should have a common multiple. In Korean, this is 공배수. 공배수가 있어야 합니다. 더해서 또 주기함수가 되려면. So we have an example of sine t times sine of pi t, and they really don't have a common multiple, so they are not periodic if you sum these two together. Okay, I think you should. It is a good property that you should think about. And I think we will move on to the next topic. So this was about the complex exponential, and more basic signals. In this time we will first look for the discrete time and then move on to the continuous time. There's a basic signal called unit step function. So it is called unit step function. And we will introduce the discrete time first for this one. I would first want to draw this function first and then give you the definition. So as it is a discrete time, we have 0 here, 1, 2, minus 1, minus 2, minus 3, and so on. So unit step function is like this. If n is smaller than 0, then it has the value of 0. And if n is bigger than or equal to 0, it has the value of 1. Okay, so in equation, and we denote the unit step as u. We will do this for the entire lecture, entire course. So un is 1 if n is bigger than or equal to 0, and un is 0 if n is smaller than 0. So this is called a unit step function. And one more thing is an impulse function. Also in discrete time first. So the impulse function is the one with the value 1 only at n equals 0. So at n equals 0, you have the value 1. So this is the value 1 and this is the value 1. And the others you get 0. Okay, so in equation, and you denote the impulse function as a delta, which we write it this way. This thing is called delta. So delta n is 1 when n equals 0, and 0 when n is not 0. Okay? So impulse function, you have only one value, and one value of 1, and the unit step you have a lot of ones. Okay? And we can relate these two. In some manners, and the first way is representing delta by the function u. So if I write the result first, then okay, here comes the result. Okay, the first one is about the first difference. And it is about expressing delta n by u, which I can express as un minus 1. And this typical equation is called first difference. We know what un is, and what is un minus 1? You shift un by the value 1, but is it to the right or to the left? If you shift these to the right or to the left, when you're confused with this kind of stuff, then you always just enter the situation into the definition. 이런 것들이 헷갈릴 때는요, 얘가 이제 오른쪽으로 평행이동하는 건지 왼쪽으로 평행이동하는 건지 이런 게 헷갈리시면은 그냥 헷갈리는 순간 그냥 무조건 정의에다가 대입을 해보세요. 그러면 답이 나옵니다. 그러니까 얘가 이제 오른쪽으로 시프트 됐다는 의미거든요. un-1이. 근데 이제 그런 것들이 헷갈릴 때가 있어요. 가끔. 저도 당연히 헷갈리고요. 그래서 그럴 때는 헷갈리실 때는 그냥 definition에 집어넣으면은 확실히 아실 수 있습니다. So if you replace n by n-1, then you just replace n by n-1. So the value is 1 when n-1 is bigger than or equal to 0, okay? Because you replace n by n-1. n-1 is bigger than or equal to 0, and 0 on the otherwise. So n-1 is smaller than 0. If we rewrite this means n is bigger than or equal to 1, and this means n is smaller than 1. And if you draw this thing, Then starting from the 1, that it has the value of 1, and the others you get 0. And now you have the picture of un minus 1, and if you subtract this from that one, so un minus 1, what do you get? So below minus 1 you have zeros and zeros, so you get 0. And from the value 1 you have 1 minus 1, so you get 0. But with n being 0, then un has the value of 1, but un minus 1 has 0 value, so the 1 remains. Therefore, if you plot the result of this difference, then you get the value 1 at n equals 0, and the others zeros at the others, which is delta n. Okay? So the first difference equation can be proved by examining the graphs of the discrete time function, and you just subtract them. And one more relationship exists between the unit step and the delta function, impulse function. That is, by expressing so on the contrary, to express the unit step by the delta step. So there are two ways. And the first one is by expressing un by delta by the infinite summation from minus infinity to n. So it goes like this. So it's all the summation from minus negative to up to delta n. Okay. So I think I may stop here, and we will continue the second way of relating unit step function and unit impulse function in the next lecture. Okay. Thank you very much for your attention today, and I will see you on the next video. Thank you very much.